Hello there. So today's topic is about uh, understanding in more detail the behavior of a diode, which is a PN junction, and we'll see the current voltage relationship of a diode. And we know that in our previous discussion, we've seen that the current and the voltage relationship between diode is given by such curve, which is an exponential behavior. Initially the current is extremely low and up to the certain voltage, which is in the case of silicon diode about zero point 0.7 volt. After that, when you exceed the voltage across diode more than this cut-in voltage, let's say VTH or threshold voltage, or also called as turn-on voltage, you have a sudden rise in the current through the diode, which is an exponentially rising curve. So it's basically a non-linear characteristics that semiconductor diode exhibits. So we want to express this relationship by means of an equation. So that equation is given by a large signal modeling, and that is called as Shockley Diode model. So let me write here. It would be written as Shockley. No. Let me correct the spelling. Shockley. ShockleY. That is Shockley diode model. And that expression can be written here is given as the current through the diode, which is I, is equal to Is in bracket xe to the power Vd upon Nvt minus 1. Vd upon Nvt minus 1. So here Is is the saturation current of a diode. The very small current is also called as leakage current of your diode. Okay. And it is in the range of, let's say it's called as saturation current, or it's also called as scale current, and the magnitude of it is around 10 to the power minus 12 ampere. And basically this current is proportional to the cross section area of a diode also. Now Vt here is called as thermal voltage, which is approximately 25 millivolts, and its value is given as kT over Q, where kT is your K is your Boltzmann constant, Q is the electron charge, T is the temperature. And then there is one more parameter, N or eta. This is basically called as diode ideality factor. So it's in the case of silicon, it is usually 1 to 2. And when you say that this forward voltage drop Vd is very, very large than the product of N times Vt, which is this value, then the formula that we are talking about, this formula, this equation, is simplified to I equal to Is e to the power Vd upon N times Vt, because this then term gets much, much greater than 1. So this is how we can actually understand the current and the voltage expression or the IV characteristics of your diode. So but this is only an approximation of the IV characteristics of a diode, right? Uh, if we want to understand the behavior of this diode, and specifically if we want to, let's say, simulate the behavior of your diode and its IV characteristics in theory, I have shown you this characteristics right here, and the equation representing this is this one. So remember, this is your equation for the diode. So what I have done here is I have taken a diode from the SPICE model library, and the part number is 1N4148. If I right click it, I see that there is a silicon diode which has a average forward current capability about 200 milliampere, and its breakdown voltage is 75 volts. So I click OK, and then across it I connect a voltage source of DC value of 1 volt. And let me right click it and click here, and here I see the SPICE model for this diode, where I see its syntax expressed by dot model, then part number is what we just talked about in theory, that is the scale current or saturation, reverse saturation current is 2.52 nanoampere, is pretty small. Then there is a series resistance Rs, then there is a N, which is between 1 to 2 in theory, we just saw, is most likely that N, that is the ideality factor, and it is in the model, it's 1.752. Then there is the CJO, that's the junction capacitance of 4 picofarad. Remember, it's a PN junction, so you have two different semiconductor material, not too different. It's a P-type material and the N-type material. They are connected together. There is a then capacitance between when it is connected there, right? Then there is a term M, TT, I average, V peak, manufacturer number, and type silicon. So that's your model. Now voltage source is connected. I am connecting a load of 1K, and now the circuit is completed. So I want to first know the operating point of this circuit. So what I'll do, I will just for a moment disable this analysis, which is by this syntax, and enable this .op analysis, which I had done earlier. I'm going to do it again for you, and then I will click run simulation. Now I have this voltages and the currents. I see there is the voltage at node N001 is 1 volt, which is this node. Then voltage at node N002 is 0.45. So obviously 1 volt minus 0.55 is the forward voltage drop across this diode. So, and the rest of the voltage is 0.45, that is an output voltage. When the diode is forward bias, I am having this current, which is 0.4 milliampere flowing through the diode. And that's the same current flows through the resistance R1, and the current delivered by the voltage source is the same in the reverse direction is shown by the SPICE. Now I know this how much current is flowing, that is 0.4 milliampere. I am going to see this behavior in terms of graph now. So what I'll do, I will enable this analysis again, dot DC, click here, and then I will click the simulate button again. Now I have this graph, so why not just tile the windows so that graph comes down here. I click now the schematic, and then I click here, I have a linear increment of the voltage varying from 0 to 1 volt. And now I want to plot the current through the diode. So I take my probe to the schematic screen where I am asked to left click the mouse button to plot ID1, that is the current through the diode. I will do that. And now you actually can see in the blue, I have the current essentially zero uh, up to the voltage, let's say 0.5 is the value of the current is from 0 to up to 50 microampere. Is still the cut-in voltage here is about, let's say 0.4 volt. And after that, I have an exponential rise in the current going up to 450 microampere. So that's the maximum current at 1 volt, what we predicted in the operating point analysis. So this is how I can get this characteristics. If I increase the volt, for example, instead of 0 to 1 volt, I sweep to 10 volt, for example, and let's see the behavior. And here you actually can see that the current is up to 9 milliampere, but this part, your current is almost 200 microampere up to 480 millivolt voltage drop. So that's how you can actually. How about I now want to simulate the reverse characteristics of a diode? For example, I will just reverse the polarity of the diode. Just Control R on my keypad, and then I am just connecting the diode again in the fashion shown, and that's it. And when I'm done, I will click the simulate button. Now here I again want to see the input voltage, that is here, and then the current through the diode. Now you actually can see what I see here. There is this current which is about let's do one thing. We'll simulate it, not the stock value of 10 volt, but rather 1 volt. And now here you see the current starts from 0 nanoampere, and then it is increasing in a reverse direction up to 1.5 nanoampere, and then it is the constant after 0.2 volt at the input at the cathode. Your current is constant up to 2.5 nanoampere all the time. So that's the maximum current, the current through the diode. So 2.5 nanoampere current value is same as what we saw in the diode model here. You see the current here is IS. This is the reverse saturation current, 2.52 nanoampere. So it's pretty decently going there, right? So if you increase the voltage more than 0.2 volt, your current is uh, about 2.5 nanoampere. So hope you understand the Shockley diode model, both theory and practical. And stay tuned for more engaging content like this. Till then, wish you happy learning.